Finding limits analytically. In this lesson, you will learn how to find limits analytically. In the last lesson, you learned how to estimate limits using graphs and tables. So in the previous lesson, you were estimating limits. In this lesson, you will actually find limits. This is also where having strong algebra skills will come in really handy. So we will find limits analytically by one of the 5 following methods. The first of which will be direct substitution, and this is always the first thing you want to check. The second method will be by factoring and simplifying, or you may have heard factor and cancel. The third step, rationalizing, and you'll either rationalize a numerator or denominator, and you'll do that by multiplying by the conjugate pair. The fourth way to find limits analytically would be by multiplying by an LCD. And the last way to find limits analytically was good old-fashioned algebra. Let's take a look at some examples on how to find limits analytically. On this slide, we will look at directly substituting in a value, a specific value into the function. So in the first example, when you look at this function here that we're trying to find a limit for, you'll notice that the restricted value, because this is a rational function, the restricted value is x equals -1. And since we're trying to find the limit as x approaches 0, there's nothing stopping us from just directly substituting this value in for x. And so over here, you'll end up with 0 squared minus 4 over 0 plus 1, with the zeros substituted in there. And then when you simplify this down, you'll get -4. So the limit as x approaches 0 of this function is -4. So these other two examples will work very similarly, with the limit as theta approaches pi of cosine theta over sine theta plus 4. So again, here's a rational function. We will get 0 when pi gets substituted in for sine here, but then we add 4 to it, which is okay. It does not result in a division by 0. So this will be the cosine of pi all over the sine of pi plus 4. And when you evaluate the cosine of pi, you'll get 1. And when you evaluate the sine of pi, you'll get 0 plus 4, which gives you 1/4. And in this last example, I just realized that the limit as t approaches -5 of square root of 5 minus x, that this should in fact be a t. So there we go. So now this limit will make some sense. So again, if we look at the domain of this square root, we know that t needs to be less than or equal to 5. And this value of -5 works here. It's in the domain of the function we're trying to substitute in, so we can just substitute it in. We can say the square root of 5 minus -5, which ends up giving you the square root of 10. And yes, you will have to go through and simplify your square roots. Since the square root of 10 is as simple as it gets, that is our answer. On this slide, we will be looking at 3 examples of factoring and simplifying. But if you didn't know that that was what's going to be happening on this page, you might try substituting in the 5 for the function here, for the x's. And when you do that, you'll get something that looks like this. You'll get 5 squared minus 25 over 5 minus 5. And if you simplify that down, you'll end up with this nice little fraction over here, 0 equals 0. And we call this an indeterminate form. Now this specific indeterminate form, 0 over 0, alerts you. This function that you started with over here, the x squared minus 25, or whatever function, when you're getting 0 over 0, can be simplified. So simplify it, and then make your direct substitution. So, if you'll remember back, the limit as x approaches 5, the numerator can be factored into x plus 5 times x minus 5, all over x minus 5. Now, we can simplify this fraction a little better. And how we do that is we can cancel out the x minus 5 with the x minus 5, and we can get that the limit as x approaches 5 of x plus 5. So we factored the numerator, we simplified the fraction. Now we can substitute this 5 right in for x. So why don't we do that? And we will get 5 plus 5, which gives you 10. So factoring and simplifying, then making the direct substitution. Another thing I must point out, if you end up taking an in-person calculus course, is that this limit notation, the limit as x approaches 5, the limit as x approaches 5, the limit as x approaches 5, you keep writing the limit as x approaches 5 until you make the direct substitution. Once you make the direct substitution, the limit notation disappears. If you go back and look at the last slide, the last 3 examples, the limit notation disappeared immediately because we were able to make the direct substitution right up front. On to example 2. The limit as x approaches 3 of this fraction. Now again, if you go through and you try to substitute 3 in for all of these x's, you will end up getting 0 over 0. So your clue here, maybe your clue here to tell you that you need to factor, is that you have a quadratic over a quadratic. So when you factor this limit, or this expression over here, you'll get the following limit. The limit as x approaches 3 of x minus 3 times x plus 1, minus 1 in the numerator, and 2x plus 1 times x minus 3 in the denominator. And down here in this fraction, the x minus 3's reduce away. And since we have not made the direct substitution yet, we will write the limit as x approaches 3 of x minus 1 over 2x plus 1. Now the direct substitution can be made for these x's here, leaving you with 3 minus 1 over 2 times 3 plus 1. And when you simplify all this down, you'll end up with an answer of 2 over 7. So to bring it back to the idea of the last lesson, as the graph of this thing approaches 3 from the left and the right, both sides are approaching the y value 2 over 7. Now I don't know how you would ever be able to tell that from a graph, so these analytic methods are much more precise and much better than just looking at a graph. In this last example, the limit as a approaches 4 of a cubed minus 64 over a squared minus 16. Again, if you directly substitute the 4 in for a, you'll end up with the indeterminate form 0 over 0. And that tells you that this fraction can be simplified somehow. With this example, you will need to know how to factor the difference of cubes. And when you factor the difference of cubes and in the denominator factor the difference of squares, you will get the following breakdown. And when you get this breakdown, you can see that the a minus 4's will cancel, leaving you with the limit as a approaches 4 of a squared plus 4a plus 16 all over a plus 4. And when you go through and directly substitute this 4 in for all of the a's now and simplify it all down, you will get that the limit is equal to 6. And again, just to bring this idea back of thinking in terms of a graph, as the graph approaches 4 from the left and from the right, the y values are getting close to 6. On this slide, we will be looking at limits, finding limits using the rationalizing technique. And I mentioned on the first slide that using the rationalizing technique means we will be multiplying by a conjugate pair. And how do you know what a conjugate pair is? Well, you find where the square root is, and generally there will be another term either added or subtracted to or from a square root. So a conjugate pair is going to contain the same exact two terms with the opposite sign in between them. So if you look at the first limit here, the limit as x approaches 3 of the square root of x plus 13 minus 4 all over x minus 3. The first thing we want to do is multiply the top and bottom by the conjugate pair of the top. Now, another way to say this is to rationalize the numerator. Multiplying by the conjugate pair will look something like this. So this red fraction here is what the conjugate pair looks like. It is the square root, the side containing the square root with the other term. So we have the same two terms here, the square root of x plus 13 and 4. Now the sign in between them is plus instead of minus. The entire point in doing this is to get rid of the square root in the numerator. So when you multiply a square root times a square root, the same radicand on the inside of the square root, you'll just end up with the insides over here, x plus 13. Then continuing this FOIL idea, the minus 4 times the square root and the plus 4 times this square root will reduce away. And then minus 4 times positive 4 is negative 16. So you may notice that in the denominator, I did not multiply anything out, and there should be parentheses around this x minus 3. There's nothing being multiplied out because that's not going to help you, especially since when you look at the numerator here and you see it simplifies into this. Simply x minus 3. The 13 and the negative 16 reduce to negative 3. And now when you look at this fraction, there's a factor of x minus 3 that we can reduce away. So this will give you the limit as x approaches 3 of 1 over the square root of x plus 13 plus 4. And now, if you substitute 3 in for this x, you will not have a divide by 0. So when you substitute that 3 in there, you end up with a fraction that'll look something like this. 1 over the square root of 16 plus 4. And the square root of 16 is 4. 4 plus 4 is 8. So the final answer here would be 1 over 8. I'm going to give you a few seconds to pause the video so you can try the second example for yourself. You will do the same process, finding the conjugate pair of the side that has the square root, multiplying top and bottom by the conjugate pair, and simplifying everything down to get a limit. In this second example down here, I want to mention again that you can try directly substituting this value in for every x. And I forgot to mention that up here. But when you do that up here with the 3, you'll end up getting a 0 over 0, which tells you that this fraction can be simplified somehow. And to simplify this fraction, we needed to multiply by the conjugate pair. Back to the example down here. Again, if you substitute in this -6 here and here, you'll end up with the form 0 over 0. So what you will need to do instead is multiply top and bottom by the conjugate pair of the denominator. And so I will slowly reveal steps as to what that looks like. So here's the final answer, -2 times the square root of 3. So first, multiply the entire fraction by the conjugate pair of the denominator. So the same square roots in the same order, opposite sign. When you do that, you'll end up with this fraction. And when you start with that fraction, the next step would be to simplify the denominator, the 3 minus x plus 9. That will turn into x plus 6, with a negative being multiplied out front. You could common factor that -1 out, and then the x plus 6's would cancel here. And this negative would come to the front, and we would just be left with this binomial with the square roots. Substitute in -6, get the square root of 3 plus the square root of 3. Well, if you have a square root of 3 and you multiply, or you add a second square root of 3, you have 2 square roots of 3 being multiplied by -1. -2 square root of 3. On this slide, we will be finding a couple limits via multiply by the LCD method. And just so I can say it one more time without writing it this time, but if you substitute 7 directly in for a here and here, you will end up with a 0 over 0, telling you that this can be simplified. So when you see fractions within fractions, like here I have 2 fractions in the numerator of this bigger fraction here. The LCD comes from these 2 fractions. So we have a denominator 3 and a denominator a minus 4. So here I will multiply by 3 times a minus 4 in the numerator of the big fraction. So this 3 times a minus 4 will get multiplied to all of this. And I will multiply by 3 times a minus 4 in the denominator. So here's what ends up happening. When you multiply 3 times a minus 4 to the first fraction, The 3's will reduce, and that'll leave you with na minus 4. Now when you take this and you multiply it to the second fraction here, the a minus 4's will cancel out, leaving you with a 3. And this minus sign is still right there. So in the denominator, we will not multiply all of this out. We will just leave it as is. The entire point of multiplying by the LCD is to get rid of the fractions in the numerator, get rid of the little fractions. So in the denominator, we will be left with a minus 7 times 3 times a minus 4. Now, simplifying the numerator a little bit, a minus 4 minus another 3 ends up giving you an a minus 7. So in the denominator, we will still have a minus 7 times 3 times a minus 4. And we still have to write the limit as a approaches 7 because we haven't made a direct substitution yet. But now the a minus 7's can cancel, and we can now write the limit as a approaches 7 of 1 over 3 times a minus 4. So now we can directly substitute this in here because we will not have a 0 over 0 situation, nor will we have a divide by 0 situation. So when you substitute the 7 in there and simplify everything down, you'll end up with a 1 over 9. Okay, on to the next example. Before I try anything mathematically, I want to point out again that if you try to directly substitute 0 in for y, you will end up with a 0 over 0, telling you that this fraction can be simplified somehow. So now the difference is the fractions are in the denominator of the bigger fraction. So the LCD here will consist of y plus 2, y minus 2. So we will come over here and multiply times y plus 2, y minus 2, and in the denominator y plus 2 times y minus 2. And using a similar idea of what we did here, distributing the LCD to each fraction and canceling things, we will do that down here as well to give a limit of this. So again, you might be wondering, how is this helpful? Well, first of all, just by looking at it, this has fractions within fractions. This is now just one fraction, so that's nice. But even better, we can simplify the denominator so that it looks something like this. We have negative y minus 2 plus y plus 2. So the minus 2 and the plus 2 reduce in the denominator, and that leaves us with 2 y's in the denominator. So the next limit will look like this. And now that we've simplified the denominator a little bit, we can, oh look, we can cancel. We can cancel a y. That's nice. So now the limit will look like this. The limit as y approaches 0 of negative 3 y plus 2 times y minus 2 all over 2. And so now finally we can substitute this 0 in for y. And when you do that and simplify everything down, you will end up with the limit equaling 6. On this slide, you will get one whole algebra example, and your goal is to cancel that. That is a delta x. This probably isn't the first time you've seen it. Maybe back in a previous course, you saw delta x used for the slope formula, delta y over delta x. But if this is the first time you're seeing it, delta x is viewed as one object. It means the change in x. We cannot split this little triangle away from the variable x. It is 1 unit. So up here in the numerator, if we square this binomial, delta x is its own unit. So when you square this binomial, you will get x squared plus 2x plus delta x squared. Now that is still all multiplied by 2, and so this is, we can distribute the negative 3 here and get negative 3x minus 3 delta x plus 17, and I'm going to distribute the negative over here to get negative 2x squared plus 3x minus 17. So this is still limit as delta x approaches 0 all over delta x. We have not canceled that yet, or reduced it away. So now I'm just going to slowly put up some steps here so you can just see how the algebra works. So at this point, I have finally reached the goal of reducing this delta x out of here. Since that was our goal, and now we have reached that goal, this 0 can be substituted in for any delta x's that are left over. So this entire middle term turns into 0. This entire limit ends up being 4x minus 3. On this slide, we will talk about the squeeze theorem. The squeeze theorem states, let f, g, and h be 3 functions satisfying the inequality f of x is less than or equal to g of x is less than or equal to h of x for all x not equal to c in some open interval containing c. So if all of this happens, and if the limit as x approaches c of f of x is L, and the limit as x approaches c of h of x is L, then the limit as x approaches c of g of x is L. Here's what that looks like in pictures. So you can see some pictures here. We have f of x is always beneath g of x, which I'll start drawing here in red, and I'll start drawing over here in red. This is g of x. So h of x is always underneath the g of x function, and g of x is always underneath the h of x function. And what the rest, so that's this first whole part of the statement up here. There are 3 functions so that this inequality is true. Check. So now let's see what happens. If the limit as x approaches c of f of x equals L, so as we approach c from the left and from the right, and we have a limit here that is equal to L, the y values approach L, and for h of x, the limit as x approaches c is also L. So as the function approaches c from the left and from the right, the y values approach L. So this function g of x that is always in between the upper and lower function, as it gets closer and closer and closer to c, it has to squeeze through at that point, which means that the limit as x approaches c of g of x is L. Very profound indeed. It makes sense if you have a function that's down here and a function that's up here, and you have a function that's always between them, and these 2 functions, the bottom and top function, the blue and black function, kind of meet at the same y value here at x equals c, then the red function also has to meet at that y value when x equals c. On this slide, we will see an example of the squeeze theorem, and we will need to use the squeeze theorem to find this limit right here. The easiest way to know that you will need to use a squeeze theorem generally is that there's an oscillating function, a function that bounces between two different y values, and another function that you can find the limit for nicely. And generally what happens is you will find that the function that oscillates, the sine function, you should recall from any trigonometric lessons that you may have had before that it'll always end up oscillating between 1 and -1. And this is really close to what we need to find this limit here. So we're building up this expression inside of the limit. The next step here is I want to multiply all of these sides of the inequality by x squared. The part of the function that we can find the limit for nicely. And this gives us a negative x squared is less than or equal to, these should all have equal to's. The sine x squared times sine of 1 over x cubed is less than or equal to x squared. Finally, we can take the limit of all of these sides of the inequality. So the limit as x approaches 0 of negative x squared is less than or equal to the limit as x approaches 0 of x squared sine of 1 over x cubed is less than or equal to the limit as x approaches 0 of positive x squared. So these outside limits are pretty easy to compute. This limit, if you directly substitute 0 in, you get 0. And this limit on the right, if you directly substitute 0 in, you'll also end up with 0. And in the middle here, we have the limit as x approaches 0 of x squared sine of 1 over x cubed. So since this limit has to be greater than or equal to 0 and also less than or equal to 0, this limit must be, way back up here at the top, 0 by the squeeze theorem. But wait, you exclaim. We've seen all of these examples about limits, and none of them have been about trig. I've got your back. So in this slide, we will be taking a look at some trig limits. And then I think on the next slide, I'll fit in the special trig limits because math. So some trig limits may look like this. So here are 3 examples of what trig limits could look like. And with these 3 examples, we can just go ahead and directly substitute these values in. So this pi can just be directly substituted in for theta. And that is because in the denominator here, the cosine of pi is -1. So there's no divide by 0. And if there's no divide by 0, then there's no chance of getting 0 over 0. So we can just substitute this in and get the sine of pi is 0 plus 6. And I already mentioned that the cosine of pi is -1. So this ends up being -6. For example 2, we have this here. If you try to substitute 0 in for p here, you'll get the cotangent of p. Maybe we should rewrite that so that it looks like the limit as p approaches 0 of 1 over the tangent of p. I'm guessing that you will know that the tangent of p when p is 0, so the tangent of 0, easier than you know the cotangent of 0. So we can rewrite this, and then we can substitute this in here, and we get an answer that ends up being 1 over 0, and this doesn't make sense. This divide by 0 cannot happen, so this limit does not exist. And then lastly, the secant, oh my goodness, this limit as h approaches 0 of secant x plus h minus 14 over 3h plus tangent h plus pi over 4. Wow. All right. So, again, I said it was something that we could just substitute this value in for h. So now there is an x in this expression, and we don't do anything to that. H is what gets substituted with 0. So the answer here will end up being the secant of 0, I'm sorry, the secant of x plus 0, which is just the secant of x minus 14 all over. When you substitute 0 in for here, this h, you'll get 3 times 0 is 0. But then we're adding the tangent of 0 plus pi over 4. So 0 plus tangent pi over 4 ends up being 1. So really, this whole limit just ends up being secant of x minus 14. And you can go back and look at the previous slide when we had x's and delta x's. When we substituted 0 in for the delta x's, the x's stayed the same. Nothing happened to the x's. On this slide, we actually get to see what the special trig limits are, and as you can see, there are 2 of them. The first one being the limit as x approaches 0 of sine of x over x is 1. And the second being the limit as x approaches 0 of 1 minus cosine of x over x is 0. And you'll be able to tell if you should be using a special trig limit because, again, if you tried directly substituting 0 in for these x's here and here, you'll end up with a 0 over 0 form. So you can see if you directly substitute 0 in for x here and here, you'll end up with sine of 0, not sine of theta, sine of 0 over 0, which is 0 over 0, which means that there's something funny happening here. It can be simplified, but not very easily, but the limit would be 1. An example of something that it would not be equal to 1 is like this one here. The limit as x approaches 0. So same setup. The sine of x plus 4 over x plus 4. And you can tell that the limit will not equal 1 here because when you directly substitute 0 in for x, you don't get 0 over 0, you get sine of 4 over 4, which actually ends up being the answer for this limit here. And so it's very similar for the limit down here with cosine. If you try to substitute 0 in for the x's, you'll end up with 1 minus cosine of 0 all over 0. And if you remember your trig values, you can remember that the cosine of 0 is 1 over 0, which is 0 over 0. So you need to double check that you're going to end up with a 0 over 0 form in order to use these special trig limits. On this slide, we will see 3 examples of special trig limits. The first of which is the limit as x approaches 0 of sine of 3x over x. And yes, if you try to substitute 0 directly in for x's here, you end up with a form of 0 over 0. But there's one problem: this limit does not equal 1. And that's because what's on the inside of the sign needs to match what's in the denominator. So we can rewrite this limit in the following way. We can multiply and divide by 3. And then we can push this 3 over with the x to get a limit that looks like this. And now, since if you try to directly substitute 0 in here for x, you still end up with a 0 over 0 form. The inside of the sign matches the denominator. We can say that the limit as x approaches 0 of this part is 1. So this 1 is what happens when we take the limit of this sine of 3x over 3x. So we're done with the limit. We already took that limit. We got 1. We have a 3 times 1. The final answer here is 3 from this 3 times this 1. In the next example, we have the limit as x approaches 2 of sine of x minus 2 over x minus 2. Now this is a strange situation. The limit is not going to 0. X is not approaching 0, it's approaching 2. But what's on the inside of the sign and the denominator approach 0 if you put these numbers in, if you put 2 in for this x and this x. As a matter of fact, it gives you a 0 over 0 form. So another way to think about this limit is in the following way. X minus 2 approaches 0. It's almost like this approach arrow that's here is like an equal sign. If x approaches 2, that's the same exact thing as x minus 2 approaching 0. Just subtract 2, and we get this idea here. So what's on the inside of the sign now is approaching 0, x minus 2. And what's in the denominator of the fraction is approaching 0. Still gives you a 0 over 0 form. And now we have the limit, as something, what's on the inside and denominator, approaches 0. This answer is just 1. In the third example, we have the sine of 3x over the sine of 5x. And the first thing I want to do here is show you what happens when you substitute in 0. If you substitute 0 here and here, you end up with a 0 over 0. And in order to use the sine version of the special trig limits, there needs to be sines divided by x's. And the easiest way to achieve that is to multiply the top and bottom of this fraction by 1 over x. So here we'll have the limit as x approaches 0 of sine of 3x over sine of 5x. If you multiply by 1 over x, multiply by 1 over x, divide by 1 over x, then we can rewrite this limit in the following way. And this allows us now to take a look back to example 1. In the numerator here, that's exactly what example 1 was like. We need to multiply top and bottom of the numerator by 3. And in the denominator, that's very similar to example 1, except there's a 5 inside the sign instead of a 3. So multiply and divide the numerator by 3. Multiply and divide the denominator by 5. And this will give you a limit that looks something like this. Again, pushing that 3 over and the 5 over with the x in the denominators of the respective fractions, you can see now that the limit of the sine 3x over 3x will go to 1, and the limit of the sine 5x over 5x will also go to 1. And so since in the numerator you have 3 times 1, and in the denominator you have 5 times 1, this limit ends up being 3 over 5. On this side, a few more special trig limits, the first of which is the limit as theta approaches 0 of tangent 2 theta over theta. Anytime I see tangent, I want to split this up into the fractions sine over cosine. So let's do that and rewrite the limit like this. So here's the limit tangent 2 theta became sine 2 theta over cosine 2 theta. Now having a fraction within a fraction is not very intuitive, nor is it pretty. So let's rewrite this again by multiplying top and bottom by the LCD of the small fraction, which would be cosine 2 theta. So multiply by cosine 2 theta. And when you simplify this in the numerator, you'll just end up with sine of 2 theta over theta cosine 2 theta. So that limit looks like this. And with this limit, it looks like there's almost a special trig limit happening here with the sine 2 theta over theta. We're just missing the 2 theta in the denominator. So in order to achieve that, we can divide the whole function by 2 and multiply the whole function by 2. And that allows us to have the following limit. I'm going to split this apart in a very special way. This is the limit as theta approaches 0 of sine 2 theta over 2 theta times 2 over cosine 2 theta. And I split it apart like this so again that you can see where that special trig limit is right here. So it's what you see over here with the 2 included in the denominator. The 2 in the numerator is in the numerator of this other fraction. And so now that we have the sine of 2 theta over 2 theta, and that this goes to 1, we can certainly substitute this 0 in for theta in the cosine. And when you do that, you end up with the cosine of 0, and the cosine of 0 here in the denominator just becomes 1. And so 2 over 1 equals 2. The limit after all of that is 2. In the next example, we have our first example of a special trig limit involving cosine. And remember that the cosine limit that we're trying to make happen here is 1 minus cosine of the inside all over the inside, as long as that inside limit is going to 0. And I just realized that these should be alphas. So this is alpha, it's just another variable. So if we're looking for 1 minus cosine of inside, we have 6 minus 6 cosine of inside. You should factor out the 6 from the numerator so that we have a limit that looks something like this. And again, this limit over here, or this expression over here, is very, very close to what we're looking for with the limit, we're looking for 1 minus cosine of inside over inside, as long as the insides are going to 0 as the limit goes to 0. And it's very close. We just need the insides to match, so we need to divide by 5 and multiply by 5. Now that we have this trig limit, we can say that this limit here, or the limit as alpha goes to 0 of this limit here, is going to 0. It approaches 0. Well, if this whole expression approaches 0 as alpha approaches 0, and we're going to multiply that times whatever we have left, 0 times 6 times 5 is still 0. So that entire limit simplifies down to 0. In the third example, the limit as x approaches 0 of x divided by sine of x. In order to see how this works, instead of multiplying by something relatively nice here, like we did in the first example, cosine of 2 theta to get rid of the fraction within a fraction, in this example, I'm going to multiply by 1 over x. Top and bottom, multiply by 1 over x. And this is going to create a fraction. So if you multiply x times 1 over x, you'll end up with a 1 in the numerator because these x's will reduce away. And in the denominator, if you multiply sine of x times 1 over x, you end up with sine of x over x. And of course, we have the limit as x approaches 0 of all of that stuff. So now you can see that we have this special trig limit in the denominator. This will approach 1 as x approaches 0. So 1 divided by 1 is 1. So now we have even a different version of the limit as x approaches 0 of sine of x over x is 1, but also the limit as x approaches 0 of x over sine of x is also 1. So this is a third special trig limit that you can include in that list from a couple slides ago. On this slide, there are 3 examples that I will leave for you to try. I will give you a second to pause the video, and then I will make sure the answers get up here so that you can check to make sure you're doing these limits correctly. Here are the answers for these 3 limits. Explanations will come soon.